Very much. Okay, thanks for coming here to attend my talk. I'm afraid I will have no Britney Spears in this one. Only maybe the sound of bits and bytes. It's not as nice, but well. We'll be talking about Flutter applications. I do not expect all of you to know very much about Flutter. Probably maybe some of you do. So don't worry, there is a very short crash course at the beginning about that, but I feel it's kind of interesting. Yeah, before I get my caught in the cables. So before we go to technical stuff, so my name is Axelle. My first name is Axelle. And I work with Fortinet, where I am a malware researcher. So my daily job is to get mobile malware and IoT malware and to dig into that, reverse them, detect them, and try to make them more easily detectable for the next times. I'm also the lead organizer of a CTF, which is dedicated to smart devices, which is called Phone. Yeah, that's the shameless advertisement there. Okay. It's in the south of France. It's a non-site CTF. It happens once per year. It will be at the very end of November this year. So if at that time you feel like coming, you will be, of course, very welcome. Our goal today is to reverse Flutter applications, okay, especially malware, because that's my job, let's say. And also one of the sub-goals is that I released a CTF challenge to GreHack, which was a conference in France in November. And it also is on the same topic, so we are going to solve it together this morning. So, before we get into Flutter, well, Flutter uses a language which is called Dart, and it's an object-oriented programming language. And the definition is just there in Wikipedia with a C-style syntax. And as you can see here, well, this is a working example with, like, hello Nullcon. I don't think it's really very complicated to read. The syntax is pretty nice, actually, to reread. What's a little bit I am both interesting and strange with it is normally when you are compiling a C program or whatever program, actually, most of the time you get only one possible binary. Here we have 4 different executable output formats that we can get. And depending on whether you want it to be small or you want it to be very fast, well, you can choose the output format which you prefer. Like, obviously, if you're using what is called a self-contained executable, well, it's going to be big, but very quick. And reciprocally, if you choose what they call a kernel snapshot, well, it's going to be small, but slow, okay? And you can choose, like, the trade-offs in between there, the way that suits you. The other thing, which is really interesting, is that, well, you are going to code to write your application with one single source code, and then you can compile that and build your application for both Android, iOS, but not only mobile platforms, you also have non-mobile ones like Windows, Linux, Mac, and it will work in all cases. Now, some of you will maybe tell me, okay, it's a little bit like Java. Well, Java is really very well portable indeed. But the difference is that, well, when you compile it, you get java.classes, which are Java bytecode. And the difference with Dart is that you are compiling natively to the platform each of the time. Okay? So this is kind of a different approach. And also the other thing also is that, well, Java on mobile platforms, it does exist, but it's not that popular. It's more for testing than anything. And here, Dart is really, well, Dart and Flutter, we'll see that later, is really well done for Android and iOS. So, Flutter. Flutter is basically the framework which sits on top of Dart. So in Dart you have, well, an SDK which comes with it, it's the language, and then you have a compiler, you have a runtime, you have debug tools and things like that. And in Flutter, you are going to have on top of that like user interface components, widgets, and a little bit more tools. With Flutter, we only have two different output formats that we can get. Now, if you get in your hands a Flutter application which is compiled for debug builds, well, you can be very, very happy because it's going to be easy to reverse because basically the source code is contained in the executable. Well, you've got to find it if it's a Flutter application. We'll discuss that later. It's in libapp.so. And, but it's going to be really easy to find the source code. If it's a release build, it's going to be actually an AOT snapshot in that case. And then, well, you're not so happy because it's the contrary. It's really difficult to reverse. It's difficult to reverse because it's natively compiled. But that wouldn't be really the difficulty because, well, hey, we've got disassemblers, right? Okay. So that's not really what makes it difficult. What makes it difficult is that Dart is compiled with strange or, well, unusual strategies which completely lose disassemblers. They are lost when they see what they, the assembly code that they have. And that's the difficulty in reversing it. The other output types, we're going to forget about them because they're not used in Flutter. So what we will focus in is those AOT snapshots, because as I said, if it's the kernel snapshot, it's too easy. We're not going to discuss it. So it's only the AOT snapshots, and also actually my CTF challenge, well, it was a Dart AOT snapshot. So that's what we'll discuss. So let's have a look at what we get with standard disassemblers. This is binary ninja, and in that case, well, it's I'm sure it's too small, yeah, for you. Here you just have actually the function name with the arguments which are there, and what we can see if you look into it a little bit more in depth is that actually it's not getting the arguments right in that case at all, and not the function name either. With IDAPRO, and actually with binary ninja as well, the other thing is that you will never see in your entire assembly code any literals, any constants, any strings, anything like that, because we'll discuss that later. They don't know how to find them in the code. Same with radar, same thing. And with Ghidra, well, it's even worse, because actually you can't read that either, but it's written undefined here, okay? It just doesn't get the entry point correctly. It doesn't find the main, and it's lost in the assembly. Well, it's kind of completely lost there. In all cases, I'm not saying that the disassemblers are useless. We will be using them, and you can, if you know how to use them, I'm sure that you can trick them. Well, you not trick them, but you can configure them better to give you some better output. But you will always have some problems with strings, with function names, and that's not only a matter of being strict or not strict. Okay. So, a few concepts about the way Dart is assembled before we get into a little bit of practice, don't worry. One of the key issues is that Dart is using specific registers. It's using specific registers for something that is called the object pool, which we'll get into just after. And also for the Dart VM thread, you've got a specific register. For instance, R14 on x86. On some platforms also, it defines its own stack pointer. Okay, so this is kind of really important. Stack pointers in assembly code, that's something you should be aware of. So on ARM64, it's going to be x15. Okay, cool. So how do we know all this? Well, actually, it's in the code. Okay, there's no documentation telling you it's this or that, but the code is on GitHub. You get there, you get into the right file, and you get all the registers, and in the comments you see what they are for. So R5, here we are for ARM32. R5 is the object pool register. This one is the Dart VM register, and things like that. You get all the explanation. An example of what that looks for and how it translates in code. So this one is in ARM64. Well, if you've been already doing some assembly, you know that at the beginning of each function, usually you're pushing things on the stack and then allocating some space, and then you'll do the real job of the function, right? So that's what it's doing here. It's actually pushing, the frame pointer and the link register onto the stack. And notice here, x15, this is our stack pointer that I mentioned earlier. Then the other thing also that it's doing is that once it's allocated some space, it's going to do some overflow check. And for that, it's using the Dart VM register, which is x26, which is there. Okay, so it really has some impact on the way our functions are going to look like. I said that I had to mention also the object pool. So the object pool in Dart, it's really an important concept where everything that is a constant, a literal, null objects, true, false, and things like that, gets into a big table which is indexed. Okay? And after that, in the rest of the code, you are no longer directly accessing your strings, for instance, but you are accessing a given index in your table. Okay? Nothing really complex there. So let's say we are on x86. The beginning of the object pool is held by register R15. If we want to go, for instance, to this object, 1457, we point R15 plus an offset. And here the relation between the offset and the index is that the index is offset divided by 8. So we're gonna be able to address the correct entry in the table that way. An example, a real-life example, this time it's in x86, is that, we have here R15 plus 1D47, okay? If you divide 1D47 by 8, you are going to get in decimal 936, so you go in the object pool, and you look at what you have in the object pool at this index, and you find, for instance, this string. And you know that at that place in the code, it was using this string. Okay, so this is not too difficult. It gets a little bit more complex by the fact that when the offset is big, it's going to be split in multiple instructions, okay? Because for instance, if we want to compute this offset, F038, it's going to be split in 2 different instructions. Like the first one is going to compute F000 by putting F and shifting left 12 bits. And then it adds 38. We know about the object pool. Now, the other thing also that Dart is doing a little bit specifically is the representation of integers. So, in Dart, you have 2 types of integers. You've got the small ones and the big ones. The small ones are called small integers, and the big ones are called medium integers. Okay, that's the way it is. Okay, bits. And you've got, in the least significant bit, an indicator telling you if it's at 0, it means it's a small integer. So that has the impact that all the other bits are shifted 1 to the left, which means that it's doubling the value. So when you see here, for instance, this code loading 75E, it's an even number, which means that the least significant bit is to 0, which means that it is a small integer. So the real kind of payload bits are the 31 other ones. You divide that by 2 and you get the value again, 943 here. So once you know it, it's not difficult, but at first when you don't know it, you're surprised because you don't understand why you're not finding all your integers, which is kind of basic assembly normally. And I'm done with the concepts. Now we're going to have a little bit of practice and a little bit of fun. So this is my Dart challenge, and the description of it is that, Pico is like the character I have in my slides, wants to open his secure fridge, and there is a password to get into there, and you've got to find the password, basically. There's a play on words there. It's a particular French one. Darty. Darty is a shop in France which sells, fridges, electronic devices, washing machine, dishwashers, and things like that. And of course, there was the word Dart in there to kind of hint people heavily that this was a Dart executable. Demo. So I'm gonna go here. We're gonna go really big. So you get that, and you've got to find a password. Obviously, I don't know what it is like that. And that's what it says. And you might notice at the end that it tells you the door is locked, because obviously that password wasn't the correct one. And you have like a table which is printed, okay, with on one side indexes and on the other one kind of lots of strings. Any idea what that could be? Yes, of course, it's the object pool. I am providing here for this challenge the object pool because otherwise people would have had to read the object pool, and that is something which is a little bit difficult. So I am providing the object pool, and now we are going to decompile the program. I'm going to load my project. And we are going to search for functions which have the word main inside there. AFL lists all functions in there. We have 2, which is kind of usual. Usually, very commonly, you have one first very low-level main calling the second one. I'm gonna go to this one, and we are going to decompile the first 20 bytes of that. I'm gonna go slightly smaller. And well, we have the beginning of our main. You can notice here, the first few lines. Well, it's very much like what I said at the beginning, the prologue of it. You are pushing things on the stack, and then you have an overflow check. Then we're printing things to the terminal. Again. And then we are asking something, okay, so probably we're asking the password here, and then we have a function which is called create flag. Now in the CTF, when you see something written create flag, obviously you've got to go and have a look, okay? So we're gonna go there. Yes, I'm gonna decompile it completely. And we will go through every single line. No, I'm joking. That's the beginning. We'll go quickly to the thing. We see that here we are allocating an array, and then we see kind of a panel of very similar instructions, where obviously we're calling register R15 with a given offset, which means that we are actually filling a table of objects from the object pool. Okay? That's because we know what R15 is. Now we go down through the entire table. We get another table, and this time, notice the difference? We are loading integers And all of them are even, so all of those are small integers. So, I don't know, let's take this one. This is the second one, 760. I'll put that probably white so that you can read it better. And we're gonna do very simple maths. 760 divided by 2 is 944, okay? And at the beginning of my other table, what was the offset? It's this one, 1D87. So this one is from the object pool, 1D87. 87. It's also 944. And if you look, no, we can't. I'm going to run it again. If you look at the table that we had there, it's that one. Okay? So actually, we are creating on one side a table of indexes, and on the other one, a table of all the values which are in the object pool. Cool. Then I'm going down, okay, because the tables are a bit long. We have a loop, and in that loop, there's really nothing really very interesting. We are just printing the table, writing the integer and writing the object. And then it starts again. We have, again, something which is reading stuff from the object pool and calling a function, then reading something else from the object pool, etc. all the time, and it's returning that. Okay, so create flag is returning something with various parts of the object pool and calling a function. What is that function? So 0078880C. Yep, it's FCN. And there you go. So we're not really going to disassemble that one, but we see that it's coming from a source code called string. So we are getting strings from the object pool. We are calling a function that operates on strings, and we've got various chunks. So what could that be? Concatenating strings. Okay? So, pretty good. Let's go back to the previous one. So I'm going to go at the beginning of this. So here we see that the beginning of our flag is obviously going to be the object at 1DA7. So we need to find what is the index for this one. 1DA7 divided by 8. That is 948. And then I have a look at the object pool in the object pool I provided, and I see that it's going to be this string. And as a matter of fact, this is the beginning of all flags at GreHack 2023. JH23. So that's how we actually compute the flag. Getting back to the slides. So this is done. And there we get the flag. So you read after that each entry from the table I've been giving, and then you concatenate everything, and you get a very nice flag. Hey, done. Well, thanks. Actually, you can congratulate yourselves. You did it. So this is for one of the goals that we were meant to have today. The other one is how about reversing Flutter applications this time? So if you get an Android Flutter application, well, if you're used to reversing Android applications, you know that they come in a package, which is called an APK Android package. In there, you are going to have a Dalvik executable, which is named classes.dex, And usually all the payload, the interesting stuff, is in that file, classes.dex. Here, because this is a Flutter application, you won't have anything interesting in classes.dex except something that is initiating the Dart environment. Okay, so it won't be interesting to read at all. What the payload is going to be in the native libraries. And the native libraries will be lib. It will be in libapp.so, and you can have that compiled for the various platforms your application is meant to run on. The issue is that in the Dart CTF, the previous one that I showed, well, I had provided a non-stripped executable, which was somewhat a little bit less complicated, although already not so simple. But in the kind of real life, when I get those Android malware for Flutter, well, they are stripped, which means that all the function names are going to be like that, totally anonymous, and not very helpful to understand what is happening. An example. We're going to work on a real example of an Android malware, which is from the family Spylone, which started less than a year ago, around May of 2023, until September, something like that. It was targeting particularly Indian people, and it was trying to trick them into getting an easy loan. You would fill an application, give some personal data to get your loan, and then it would just blackmail victims. And even before they would actually get the money, sometimes they would harass them and send SMS like, yeah, you keep doing it. I am ruining your wife's honor by going viral. Okay. I am making the WhatsApp number of your wife's father house viral, etc. Harassing people so that they pay back the loan with lots of interest even before the end of the loan. Okay. So, how is it implemented? Well, it's an Android application, so it has to start from the classes.dex. In there you've got the real main, well, the entry point, let's say, and it is initiating the Flutter environment. And then in the Flutter environment, you've got your Flutter application with all it needs to do. And here the malware authors decided to implement some of the functionalities on the Java side. Like, for instance, the way to retrieve contacts or to retrieve SMS information. Well, that was implemented on Java side. So if we want the Flutter malware to call these, well, we need to use what is called a method channel. This is the way to discuss between both worlds. Okay. Now, reversing this part is not particularly difficult. It's like standard Android reversing. Okay. So there are lots of other talks for this one. Here, in this one, we will focus rather on how to reverse this part, the part that is actually going to call the parts in Java. Okay, so the Flutter part, which is calling the Java parts. So I thought, okay, who in Flutter is calling, for instance, Go repayment URL? So I didn't have really any clue. I am using here a decompiler which is called Jeb, which is pretty much specialized for Android, but not only. And actually it is useful to me because it is able to read the object pool of Flutter applications. Okay. So I thought, okay, I'm going to search Go repayment URL, and I see that I only find it once in the object pool. I don't find it in the assembly code, only in the object pool, and at index 8727. That's obviously a big offset, so if I want to find who is using that, well, I'm going to be, unfortunately, in the case where I have that split on two lines, two instruction lines. So then I search again. Where can I find either of these lines in my assembly code? Of course, there are many hits, especially for the first one, shifting by 8. So I was a little bit unlucky, But in the end, I found the one with B8, and where we had exactly both steps which were happening. So I found the Flutter function, which is calling the Java side go repayment URL function. Good. So now I would like to find what is the name of this function in Flutter, okay? Because I just have that name, sub 4093F4, which is not really meaningful, okay? The executable is stripped, but with Jeb is able to read part of the Dart AOT snapshot and can supply some information on the offsets and of each function names. So I search for that. I search for the offset, and I find one method which is called goRepayURL. So actually my function name in Flutter is goRepayURL, and it calls in Java goRepaymentURL. I mean, both names match, so it makes sense. So that's how it works. So that's how to start and do all the stuff. We can do it for get device contacts, for get SMS information, and all the stuff to understand how and in which case it is calling this or that function. So the good thing is that with Jeb we are able to read the object pool. We are able to find cross-references for those strings by doing some search in Jeb. It's a bit manual, okay, but we are able to do it. And we're able also to find function names, what we see in the code information as well. Now, Jeb is a paid software like IDA Pro, Binary Ninja, I guess also. So are we lost without Jeb? Well, no, there is still hope. Okay. Well, there is hope in only one case. If you have an Android application for ARM64 and not a too old one, okay, well, then you can use an open source tool which is called Flutter, and which does an extremely good job at reading the object pool and providing also the assembly code, which is kind of annotated for with each object of the object pool. I'm going to show you that. So we're going to get out of that, and I'm going to put this one. So this is the output that Flutter, maybe that's easier like that, yeah. That Flutter output for that Android malware spyloan. So I told you we're going to look for goRepaymentURL, goRepayment, for instance, and the object pool is dumped in that file pp.txt. And you find it in there, goRepaymentURL, at this offset in the object pool. Now, if you have memories of numbers, actually I found it with Jeb at 11.0b8, not C0. It seems there's always a difference of 8 between Flutter and Jeb, and I don't know why. But once you know it, I mean, it's not like that. Then I can look also for the function name. So I said that it was at which offset? 3F93F4. 3F93F4. I'm not sure it's capital letters or not, so I'm going to do that. And it's nearly good, except I need to print some context. And there we have it. Okay. Our address, our function at that address, 3F93F4, well, it's called goRepayURL. And I can go and have a look at that function, Flutter. So it says that it is in a function name plugin, the Dart. goRepayURL. There you got it. You got a little bit of information. Like here, it tells you what object it is getting from the object pool. And it's even better than Jeb for that, because Jeb only finds strings. Here it can tell you it is accessing a list of 5 elements at that particular index. It provides you the names of each functions. It just makes the mapping in the assembly code, so that, well, it's a little bit easier to read. It's still a little bit of work, but it's a little bit better. Okay. And I'm nearly done. So, that's the demo. Yeah, I showed that, and I showed that one as well. So we have normally unlocked our both goals, Android malware reversing for Flutter applications, and the GreHack challenge. To conclude, whenever you get an executable for Flutter, so if you get a kernel snapshot, be happy, because you don't have anything to do, basically. It's very easy. If you have an AOT snapshot, well, if it's ARM64, I suggest you try Flutter, because it will probably help you out very much. If you have another architecture, well then, if you have Jeb, it's okay, because you can read the object pool. If you don't have Jeb, if it's not stripped, well, at least you will be able to recover function names, and that's about it, but it will be at least a little bit probably helpful. If it's stripped, you don't even have function names and you don't have strings. I think I say that you just have your eyes to cry. I have no solution for you yet, okay? Hopefully all tools, all disassemblers, IDA Pro, Binary Ninja, Radar, and everything, they are going to tackle this problem and help us out disassemble those malware. But for now, it's very painful. And thank you very much for your attention.
Thank you. Are there any questions? Yes.
Yeah, thank you for the talk. There are plenty tools for static Android app analysis, I think, so like MapSF and so on, but they all seem to lack features for shared object files like Flutter, I think. Do you have any tips on static analysis of Flutter apps?
So yeah, the tools, MapSF and etc. are not going to help you out any better, unfortunately, for that side. So you're asking for other hints for Flutter. Well, I wish I had other ones, but I don't really. It's very much in progress currently. I have written a plugin to handle the small integers in Radar, but it's so basic, my plugin, that I'm not releasing it. I mean, it's no interest. The owners of Radar will do far better in just a few weeks, I'm sure. So,
thank you.
You're welcome.
Any more questions? Well, thank you. I think we're done.
You're welcome.